we're going to talk about DeMoivre's theorem. Powers of a complex number can be achieved by repeatedly using the multiplication rule. Do you remember what the multiplication rule was? That's where if we multiply two complex numbers written in this trigonometric form, then we multiplied their moduli and we added their arguments. Remember, moduli was the r value, which we got by, if you had our complex number z equal a plus bi, your r was a squared plus b squared under square root, and we knew tangent theta was b over a, where theta was the argument. If I have a complex number written in trigonometric form, z equal r cosine theta plus I sine theta, and I want to multiply z with z, that is the same as z squared. So I just write z in its trigonometric form twice. Now notice I multiply the moduli and I add the arguments, so the theta plus theta becomes 2 theta, and so on. If I want to do z times z squared, I would take z squared, which is r squared cosine 2 theta plus I sine 2 theta, times another z, and I multiply the moduli, so I get r cubed, and I add the arguments. 2 theta plus another theta is 3 theta. I can continue this process. You can see that z to the fourth is r to the fourth times cosine 4 theta plus I sine 4 theta, and you can continue on and on and on. If we do this in general, we end up with something called DeMoivre's theorem. Z equal r cosine theta plus I sine theta is a complex number. If n is a positive integer, then we can raise z to any power n, and here's it written in trigonometric form. To do so, we take the modulus and raise it to the n power, and we take the argument and multiply by n. So let's try one. The example says, use DeMoivre's theorem to find negative 2 minus 2 root 3i, that complex number, cubed. So we're actually going to do it two ways. We're going to do it with this theorem, and then we are going to do it just by cleaning up complex numbers. So the first thing we need to do here is figure out what a is, figure out what b is. Do we see that a is negative 2 and b is negative 2 root 3? So let's find r. R is a squared plus b squared under a root. So that is what? Negative 2 squared plus negative 2 root 3 squared. All of that under a root. So that's what? 4 plus. Okay, this is 4 times 3, so 12. So we end up with the square root of 16, which is 4. So r is 4. Then we find the argument. We know tangent theta is b over a, so that is what? Negative 2 root 3 over negative 2, which is root 3. So we ask ourselves, where is tangent theta equal to root 3? I'm going to rewrite it in terms of a trig form that I know. Root 3 over 2 over 1/2, those are the ratios I recognize, and I know that's sine over cosine, and I know that cosine always goes in front, sine always goes in the back. And I know, if I remember my little form, this is my terminal point on a unit circle, 1 plus 2 is 3. So all my multiples that reduce to pi over 3 look like this. So let's take a second and plot the original complex number z to see if we can figure out what quadrant it's in, and that will help us decide what multiple of pi over 3 we actually have. So remember that your imaginary axis was our y-axis, and we used the x-axis to be the real axis. So we plot this negative 2 in the real and negative 2 root 3 here, and we know that 3 is between 1 and 4. If we take the root of all three pieces, we know that root 3 is between 1 and 2. So I'm really multiplying a number that's a little bit bigger than 1 but less than 2. So I'm going to kind of go 1, 2, 3, 4. So just kind of eyeball it, maybe somewhere like this. Okay. And I know that this is 3 pi over 3. That reduces to pi. And I'm in this quadrant, like right here, so I guess I'm at 4 pi over 3. So if I rewrite my z, I see I end up with 4, and then cosine 4 pi over 3 plus I sine 4 pi over 3. So that's my complex number. Now I want to cube that. So here I'm going to use my formula here. So z cubed is going to be, if you can still see the formula, I'm going to do my modulus to the fourth power, so I'll have, I'm sorry, to the third power, 4 cubed, and then I'm going to take my theta, my argument, and multiply by this 3 right here. So I'll have cosine 4 pi over 3 times 3 plus I sine 4 pi over 3 times 3. And I'm going to get, oh, this should say 4 cubed. I don't know what happened there. 4 cubed is 64, and I get cosine, what is that? The 3's will cancel. Cosine 4 pi plus I sine 4 pi. So this is my z cubed. I can write it this way if I want to leave it in the trig form. But let's actually simplify it. So z cubed is 64. Cosine 4 pi is 1. Sine 4 pi is 0. So I get 64. Now let's check it. Let's actually take that complex number and cube it and see if we do indeed get the same thing. First, let's square this complex number. We know that if we have a minus b squared, that's a squared minus 2ab plus b squared. So we square the first, we get 4. We multiply these together, so we get a positive 4 root 3i, and then we multiply that by 2. So plus 8 root 3i, then we square the back term. So we get 4 times 3, we get 12i squared, so this is 4 minus 12 plus 8 root 3i, which simplifies to what? Negative 8 plus 8 root 3i. Okay, so now let's take that complex number, negative 8 plus 8 root 3i, and multiply by z again. Let's FOIL it out. 16 plus 16 root 3i. Looks like we have another plus, or minus rather. Minus 16 root 3i. Looks like we have minus 16 times 3i squared. So that's what? 16. Okay, and these guys are going to cancel. I end up with 16 times 3 minus 48 I squared, but we know I squared is positive 1, is negative 1, so I have 16 plus 48, and yep, that is 64. So we confirmed it by cubing our complex number, but here's doing it with the trigonometric form.